For the first part, let's take a look at the background of Black-Scholes formula. Suppose the stock price follows a geometric Brownian motion. ds equals to mu s dt plus sigma s dwt. Wt is the standard Brownian motion, and the derivative v is a function of s and t. And by using Ito's lemma, we can get dv equals to the first order partial derivative of v2t plus sigma s, the first order partial derivative of v2s, plus 0.5 sigma square s squared, second order partial derivative of v2s. This summation multiplied by dt plus sigma s, the first order partial derivative of v2s, multiplied by dwt. Let us consider a self-financing portfolio pi, which equals v minus first order partial derivative of v2s multiplied by s. Then we can get d pi equals to dv minus the first order partial derivative of dv of v2s multiplied by ds. And we can replace dv by the formula we get from Ito's lemma here. So this portion is all from the Ito's lemma. And ds, we already know it is a geometric Brownian motion, so we can replace it by mu s dt plus sigma s dwt here. Surprisingly, we find out dwt is eliminated out. So this portfolio does not contain a diffusion term. Thus, this portfolio is a risk-free portfolio. So, by no arbitrage theorem, the portfolio must have a risk-free return. That is, this function here. The risk-free return we suppose it is R, and multiplied by this portfolio must equals to this portfolio's return. Then we can get the Black-Scholes-Merton differential equation, which is here, listed here. And this is the basic foundation for Black-Scholes formula. The Black-Scholes formula is the result of this second order partial differential equation. Because of the time limit here of this video, I would like to skip this deduction of Black-Scholes formula and look directly into the Black-Scholes formula. The Black-Scholes formula, here we can get it. The result is C equals to S n d1 minus K e exponential minus RT multiplied by n d2. And for put option, it is K e minus RT n minus d2 minus Sn minus d1. d1 here is natural log of S to K plus risk-free rate plus 0.5 sigma square t divided by sigma square root of t. d2 equals to d1 minus sigma square root of t. So this together is the Black-Scholes formula, and n stands for the cumulative distribution function of a standard normal distribution, and S is the stock price, K is the strike price, R is the risk-free rate, T is the time to maturity. Then we will look into the assumptions behind this formula. First, the stock pays no dividends, but this assumption can be relaxed. If there is a continuous dividend of Y, then the core Black-Scholes formula is the stock price multiplied E minus YT n d1 minus strike price RT n d2. This is new Black-Scholes formula. under relaxed first assumption. And the second assumption is that the risk-free interest rate is consistent unknown. And this can also be relaxed, but this will be more difficult for us to deduce the Black-Scholes formula under this relaxed assumption. And for the third assumption is the stock price follows a geometric Brownian motion. Here is the fundamental assumption under which we construct the Black-Scholes-Merton equation. So this is the most important assumption here. And the fourth assumption is there is no transaction cost. The process of short sale can be fully invested. Fifth, all securities are perfectly divisible or can be divided perfectly. This can be achieved if we have a large volume of funding, and suppose we have $1 million or $100 million, and we can divide our portfolios into many different small parts, in which every part we can buy it from the market. And the sixth assumption is there is no risk-free arbitrage opportunity, which is also very important here. Finally, we will look at an example here. Here,